All right, Unit 7, Notes 2 is all about the different characteristics of waves. So we're going to take a look at a lot of different characteristics of different types of waves. So we'll be looking at mostly transverse and longitudinal waves. So if you don't remember what those are, just recall from last notes. Transverse waves are like the ones that you see here, the ones that go up and down like this. And longitudinal waves are going to be the ones that kind of get compressed. They're going to be the compressional waves. So we're going to jump right into this. I'm going to go ahead and hide here and just jump straight into the notes. So amplitude is the first characteristic of the wave that we're going to discuss. And what an amplitude is, it is the greatest distance that the individual particles are displaced from their resting position. So what you can see here is that let's imagine we had a string, and that string's resting position was going to be this white line over here. And if we start vibrating this string, you can actually see that the wave will go up and down like this, and that will point to the amplitude. Now, the amplitude here is this orange and this blue line going to this crest and to this trough. And why it's both of them is because amplitude should be the same on both sides. And the thing that you should know here is that the larger the amplitude, the larger the energy required. So the bigger the wave, the bigger the energy that you need to put into the system. So for instance, if this was a sound wave, you would need to require more energy to increase this amplitude. So if you're listening to my voice, for instance, or to music on an iPad, and you notice that your battery is draining, one thing that you could do is lower the volume to lower the amplitude that it produces. It would still produce the same pitch and everything, and we'll talk about what that is later, but it would be at a lower volume or a lower amplitude, so it would use less energy. So the larger the amplitude, the larger the energy, smaller amplitude, smaller energy. Now the amplitude is measured at the height of the crest or the lowest point of the trough to that center line. It is not the measurement from here to here. We'll talk about what that is later. That's just called the wave height. But the amplitude is the measurement from this line right here to the very top. So that's a positive amplitude, and that's a negative amplitude. Let's go back really quick. If this was like a positive 5, this would be negative 5. This was positive 2, this would be negative 2. So just to one more time reiterate that the amplitude would be the same on both sides. The next characteristics that we're going to look at for amplitude is amplitude within a compressional wave. So you can see here that there's a compression, and the part where it's spaced out, that's called a rarefaction, if you recall that from last lecture. And for a longitudinal wave, the amplitude is measured as the density of the compression. So it's the measurement from, if we take a look at this this pinkish magenta box, from this end to this end over here. Basically, how much is that wave being compressed, right? The next characteristic that we're going to take a look at is something called the wavelength. And we discussed this a little bit in last lecture, what exactly a wavelength is. Wavelength is the length of one wave. So it's exactly what it sounds like. It's the measurement from one crest to one crest, or one trough to the next trough, or two parts of a wave that are identical. So you can see here, like this part right here is identical to this part right here on this wave. So that's the measurement of a wavelength. And it's the distance between two equivalent points on a wave. Now, for your sake, I would definitely suggest you just focus on either the crests or the troughs, because it's very easy to get confused. If you say when it hits the midpoint, well, it hits the midpoint right here as well, but that's not a wavelength. That would be half of a wavelength. So do either crest to crest or trough to trough, and that's probably the best way to measure a wavelength. And like I mentioned, usually measure between two crests or troughs on a transverse wave. But on a longitudinal wave, it's measured a little bit differently. On a longitudinal wave, it is usually measured as the distance between the starting point of one compression to the starting point of another compression. So anything within this green arrow would be considered one wavelength on a compressional longitudinal wave. One more thing I want to note here is that wavelength is usually abbreviated in formulas with this weird symbol here. This is a Greek letter called a lambda, and this is the way we are going to write the abbreviation for wavelength whenever we have math formulas involving that. Right? One thing that I want to emphasize here is that when we're talking about the energy of the wave, the amplitude and the wavelength are two things that directly impact the energy of the wave. The shorter the wavelength, the more energy is required to produce that short wavelength, or the higher the energy it has. So a shorter wavelength, higher energy. And we already discussed earlier in this lecture, the larger the amplitude, the higher the energy as well. So, like for instance, if we're talking about volume, the larger the amplitude for volume, the higher the energy would be for that. And the shorter the wavelength, also the higher the energy. All right, the next characteristic for a wave that we're going to talk about is frequency. And you might have heard this word used pretty often in just normal language, where frequency could be like, well, someone might ask you, how frequently does this happen? When it refers to the exact same thing in waves. It is the number of wavelengths that pass a given point in 1 second. So that's how we classify frequency. It could be calculated using the following equation. This is actually a pretty useful equation. It's the number of waves divided by the number of seconds. So let's say you were counting waves in an ocean, and you set a timer for 10 seconds, and you counted 20 waves in 10 seconds. So you'd have 20 over here on the top and then 10 on the bottom. Your frequency would be 2, or 20 divided by 10. And the unit for that would be hertz. So the frequency would be 2 hertz, and that's how you would measure the frequency. Notice the abbreviation for frequency is a lowercase f, but it is measured. The unit for measurement is the hertz. So don't confuse those two. You would put f is equal to 2hz as your final formula. So here is an example problem. Let's try to do this together. If a human voice produces 15,000 waves in 2 seconds, what is the frequency? So let's go back here and take a look at this formula. Number of waves divided by the number of seconds. You would just calculate that number of waves, 15,000 waves in 2 seconds. If you were to pull out a calculator, the answer you get would be 7,500 hertz. And that's what you would get. So F with 15,000 waves up here over 2 seconds, 7,500 hertz. So that's a great example of how you would find the frequency of a wave. Now, how does that correspond to sound waves? Well, sound waves, of course, come in different pitches. That's what we know them as. And frequency and pitch are kind of synonymous, where a high pitch would be a very high frequency, and a low pitch, like a bass note, would be a very low frequency. Okay, moving on. The wave period, or a capital T, that's how it's abbreviated, is calculated for time. So T for time. The wave period is the time that it takes for a complete cycle or a wave oscillation to occur. And it's usually measured in seconds. So that's how we're going to notate it. It's measured in seconds. And it's actually kind of easy. If we go back to this formula where we say frequency is the number of waves divided by the number of seconds, period is going to be the number of seconds divided by the number of waves. So it's the exact opposite of frequency. It's the inverse of frequency. Frequency and period are related, whereas frequency is the inverse of period, and period is the inverse of frequency. So before I gave the example that if we had 20 waves in 10 seconds, we had a frequency of 2. Well, if we had 10 seconds for 20 waves, that'd be 10 divided by 2. That would be a period of 0.5, which means that it takes 0.5 seconds for every wave to pass by. All right, and the last thing we're going to show here is a graphical representation of wavelength and distance, and then also period and time. So just keep in mind that whenever we graph wavelength, distance is always going to be on the x-axis, and the wavelength is going to be measured like that. So we can measure the wavelength going from one crest to another, or one trough to another, or one starting point like this to another. That would be an example of a wavelength, and it's usually measured in meters or some unit of meter, like a centimeter or a nanometer. And then if we're measuring wave period, just keep in mind that time is always going to be on the x-axis, and the distance between the crests or troughs will be the wave period that occurs. All right, so what we're going to do now is practice problems 1 through 7 You can try doing these on your own, and then we will publish a separate video on the practice problems 1 through 7.